Alright folks, welcome back. So we are taking the kind of unusual step of pausing before we get through all the content in this module to review a couple of examples. And the reason why is, again, this hypothesis testing process is super important. It is the core of what we are going to do going forward. So I've kind of sloppily written the 5 steps behind me. I would recommend you have some kind of a cheat sheet, whether it's your textbook, whether it's something you've printed out or written down. But here are those steps again. So if you remember from the end of our description of the process, the first 3 steps are defining the characteristics of the test. We figure out our hypotheses, our null and alternative hypothesis. Again, there's only a few different forms that takes. This is something that you'll have to think about the first few times, but eventually you should be able to just zip right through it because there's only a few forms that it takes. And again, this two-tailed test here is by far the most common form these hypotheses will take. You should know what those hypotheses mean, though. There'll be conceptual questions too. Then we describe the characteristics of the comparison distribution. That's basically the range of outcomes we'd expect if the null was true. That's what we're going to place our actual result on. Again, the 3 things that we need are measure of central tendency, which is the mean, measure of variability, which is the standard deviation for single scores, or the standard error for sample means, usually going to be sample means, and the shape of the distribution, which is just, at this point, say it's normal. Step 3, those threshold or critical values, again, I'm going to provide those for you. So you really just have to copy those down, but the actual basis there is where are the edges of our region of rejection. This is based on the alpha level we choose and whether it's a 1 or a 2-tailed test. Then we calculate our test statistic, which in this case is going to be a z-score. Over here, if you can see it, that's the z formula for sample means, which is most of what we'll be working with. Notice we have the sample mean minus the population mean, and now divided by the standard error. You need to know that that's the appropriate z formula for this type of problem when you're dealing with a sample mean. Even if you're dealing with an individual score, as I believe we will in this first example, you can just treat the individual score as the sample mean, and the standard deviation can be plugged right in for the standard error. So calculate that test statistic, then we just make a decision, one of 2 decisions. We contrast the test statistic with the critical value. If the test statistic is beyond the critical value, that means the result has a lower probability than the alpha, and it means we reject the null. If it's not beyond the threshold, we fail to reject. So let's look at this, basically how this premise applies to a hypothetical situation. So let's say it's 10 years in the future and you're working as professional statisticians, as I'm sure you're all daydreaming about doing as you're getting into this stuff. And let's say somebody walks into your office and says, hey, I'm looking for statistical proof for my special psychic ability. You're saying, well, all right, well, what ability is that? He says, I can tell if I'm standing in front of a really unusually intelligent person, even if I don't talk to them or look at them or do anything like that. You say, well, are you detecting anything now? And maybe he kind of looks at you funny, and you say, all right, moving on. Let's see if we can come up with some kind of evidence for this. We can construct a hypothesis test to see whether or not your ability appears to be supported. So here's what we can do. We could take them to a stadium full of randomly selected people. Let's pretend we got tons of money. We get a stadium full of randomly selected people from the entire population. Half of them are above average, half of them are below average. They're distributed the same way that IQ scores are distributed. So their intelligence levels they mirror the overall population. For simplicity's sake, let's say we just have him pick one person. Normally he'd pick a bunch of people and we'd average them together. But just to make this first example easy, we'll just have him walk around blindfolded and stop in front of one person he thinks is unusually intelligent. So how do we know if he's successful? The odds are 50-50 he's going to pick someone above average in intelligence, but 50-50 isn't really great. When there's a 50-50 shot something can happen due to a fluke, you're not going to have much confidence if you pick someone who's just above average. So they need to be a little ways above average. But how far? Well, we can use our hypothesis test to test this. IQ tests are fortunately a heavily standardized variable. They are designed to have a population mean of 100 and a population standard deviation of 15. They also follow a normal curve. If you're paying attention, by the way, notice that we already have pretty much the 3 pieces of information that we need for step 2 right here. So again, IQ scores are normally distributed. Picking someone who's just above average is a 50-50 proposition, but picking somebody who's really far above average gets less and less likely the farther away you go. So by default, our null hypothesis would be that this guy does not have any special ability at all. Maybe he's lying, maybe he's just kind of mixed up, but he doesn't have this psychic ability. So we start with that as our null hypothesis. we're going to see if this blindfolded person continually picks people who are really unusually high in intelligence and in such a way that it's really unlikely he'd do it by chance. We would reject the idea that they have no special ability. We would reject that null hypothesis. So we actually have enough information here, with only a couple of exceptions that we'll fill in quickly, to actually resolve this hypothesis test. So in step 1, we identify our populations and our hypotheses. Population 1 is generally the one represented by our sample. This would be people picked by our supposed psychic, our supposed expert. So in most cases, again, that would be a sizable group of people. Here it's just one individual, but either way, we're using a sample to represent population 1. We'd love to measure all population 1, can't do it. Population 2 is our basis of comparison. That's people overall, just generically people. And notice that we have the IQ scores for population 2. So our null hypothesis is essentially that this guy does not have the ability he claims. Remember, he claims his abilities in one specific direction. He has something of a directional hypothesis. He doesn't think he picks people of unusual intelligence, but unusual high intelligence. So our null hypothesis is all the other possibilities. The population 1, the people our expert picks, will not have a higher IQ than population 2. So mu1 might be equal to mu2, but also if he kept picking people of unusually low intelligence, that also isn't consistent with his professed ability. So that would also not support his idea. So by default, we're going to believe this. Population 1, the people he picks, doesn't have a higher IQ than population 2. Again, we'll see if we have enough evidence to throw that out. The alternative or research hypothesis is just what's left over. It's what our supposed psychic actually thinks will happen. Population 1, the people he picks, will have a higher IQ overall than population 2, a higher average IQ. Mu1 is greater than mu2. That means he does have this special ability to consistently pick people with higher average IQs than the general population. So that's our premise, but we're going to believe this guy doesn't have any ability unless we see enough evidence to rule it out. Let's see what step 2 looks like. Again, notice that you already had that information provided. We fortunately have population data on IQ scores overall. That population has a mean of 100, a standard deviation of 15. Notice we don't have to convert it to a standard error because we're just dealing with one person in our sample, but normally we would. And then we just have to identify that it follows a normal curve. Those are the 3 pieces of information you'd need to get all the credit on this step. So pretty straightforward here. Step 2 is going to get a little trickier as we move into different types of data sets, but for now, you're just copying out information you've got. Then you find the threshold or critical value on that comparison distribution. So remember, as real researchers, we'd be deciding in advance what the alpha level was. And say, okay, how extreme do scores have to be to reject the null? Well, they have to be scores that are extreme enough that it's pretty unlikely we'd get them due to chance if the null was true. Again, that's where that comparison distribution comes in. It helps us define where those unlikely scores are. So that's the alpha level. The alpha, again, is that key probability that's used to determine whether scores are significant or not. Scores less probable than alpha are considered significant. Scores that are more probable than alpha are considered non-significant. So we're going to pick an alpha of 0.05. That's pretty standard. Then you can do this little drawing like we did in some of our normal curve exercises if it helps to actually visualize where things are happening, or we can use the normal curve table. We can use that normal curve table and just say, okay, what z-score has 0.05 in the tail? And what you'll find is that it's between 2 z-scores, but as we mentioned back when we talked about z-scores, in that case we use the one that's farther from the mean. We set a slightly higher bar for rejecting the null. So basically, to be in that most extreme 5%, you need a z-score of 1.65 or greater. Those z-scores happen less than 5% of the time due to chance. Another thing to note, we've defined this as a one-tailed test. Why did we do that? You can go back and look at the hypotheses and see that we have a directional hypothesis. Our alternative hypothesis is not these 2 means are different. It's this mean is higher than this other mean, that the person is picking unusually smart people. Those are the 3 steps where we set up the test. Then we just calculate our sample score. Notice we don't have the sample score yet, so let's bring it in now. So let's say we take our expert to this stadium, they walk around blindfolded, they stop in front of a person and say, this person's unusually intelligent. You get their IQ, that person had an IQ of 120. That's good, that's above average, that's substantially above average. But let's calculate the test statistic for that person. Where do they actually fall in that comparison distribution? So here's what we use. We use the original score, which is 120. We use the population mean, which is 100. We use the population standard deviation, which is 15. And again, normally that would be converted to a standard error, but we're not doing that because it's just one person. Plug all those numbers in. 120 minus 100, this person is 20 points above average in IQ, divided by the standard deviation. 120 divided by 15 is 1.33. This person is 1.33 standard deviations above the population average. So they are above average, and they're substantially above average. Is that enough to reject the null? Again, here's what we do. We take our test statistic from step 4, 1.33. That's how far above average they are in terms of standard deviations. We take our critical value, our threshold from step 3. We need a score of at least 1.65 to be in that top 5%. They need to be at least 1.65 standard deviations above average. So you can even draw this out on a normal distribution. If you draw a line where the threshold is, and then you draw a line where the actual z-score, the actual test statistic is, you'll find that the test statistic is pretty close to that threshold, but it's not over the line. If it's not over the line, that means the correct decision is to fail to reject. So we consider the null to be true unless we see enough evidence to reject it. We decided in advance that that evidence would be a z-score greater than 1.65 because those scores have less than a 5% chance of happening. But the observed z-score is 1.33, which is close but does not count. So we fail to reject or retain the null hypothesis. This doesn't mean that we proved that this guy is not psychic. It just means we're stuck with our default where we just shrug and say, there's not enough evidence to conclude this guy is a psychic. That doesn't mean he definitely isn't. It just means that we do not have conclusive evidence to throw out the default idea that he does not. We're going to remain skeptical of psychic abilities, and that's good life advice for everybody there. So that is our first example. Hopefully it mostly made sense to you. We're going to go through one more example together in our next video.